here we go. This is a big step forward for you. Wait, what? Take them yourself. What, you can't write your own notes? You know you're going to have to write your own notes in a lot of classes, right?
You know, we're educating
Hey, Josh. Is that enough duration?
All right, here we go. Alternating series. This is large. It's actually, he's doing it over 2 lessons, an introductory lesson. Today it's pretty soft, and then like it's there over 2 more sets, or maybe 3 more sets. I think it's 138. All right. So let's start off with what you might be familiar with. You have seen alternating geometric series, to be sure. For example, 16 minus 8 plus 4 minus 2, dot, dot, dot. If I were to sketch the partial sums, notice I said the partial sums, not the term. Then the first partial sum is 16. 16. First partial sum is 16. Second partial sum is 8. 2. Okay? Third partial sum is 16 minus 8 plus 4. 12. Fourth partial sum is that 12 we left off with, minus 2. 10. The fifth partial sum would be the 10 we just had, and the next term is plus 1, so 11. Now you can see then that with an alternating negative, you get a little oscillation, which we'll talk about in a second. But if we were to find the infinite sum, it looks like it's converging around 11-ish. We'll see. But first of all, can we agree that this is a converging geometric series? What is the common ratio? Negative 1/2, which the absolute value of which satisfies the condition for convergence. So the sum is a1 over 1 minus r, or 16 over 1 minus negative 1/2, which is 16 over 3/2, which is 32/3. 10 2/3 sounds about like what we were heading towards, right? Yeah. All right then. That said, an alternating negative comes in a lot of forms. You don't necessarily only see it in geometric. That's an example. There's another example. I guess I did put this in my notes, but I should have. What do you think about something like this? Doesn't even matter what the rest of it is. How does that grab you? This goes to really true high-level numerical sense of what exponents mean. Okay? What kind of graph? Okay.
It's like an oscillating Cupid graph.
Okay. Let me go here. What happens when x is 1/2? When x is 1/2, you square root of negative. You just broke that. Okay? So is that function continuous? No. It is not. You would see a whole lot of little dots, and any fractional exponent or any decimal exponent that was even would be non-existent. Negative 1 to any even number would not happen. Okay? So this would be a sporadic, kind of dotty graph. It would be discrete. It would not be continuous, and therefore you would not integrate. It would never happen. Okay? Now that said, for series, because we're dealing with whole numbers, no big deal. we're never going to see negative 1 to the half there. That won't happen. So you'll see this in series, but you'll very rarely do an integral test with a series like an alternating negative, okay? I can't even think right now of a condition where you would. So these are cases or examples. There's nothing to do there. I will say this, the divergence theorem still applies. It doesn't matter that the terms are alternating. The terms still have to go to 0 for it to have a chance. So that's still there. Otherwise, it could go to negative infinity or spiral out of control in both directions. All right, so let's talk then about getting into how does an alternating affect other series. What does alternating do to convergence? Does it help it? Does it hurt it? Does it make it more likely, less likely? Let's go there. Let's say the harmonic series. Now, I gave you a table just to save time. I did the table for you rather than pick up the calculator. So here's the harmonic series. You can see I'm taking the infinite limit of, these are the partial sums as we gain more and more by powers of 10. Although it grows pretty doggone slow, it does grow, and it never tops out. And so no matter how much you tried, the harmonic series continues to grow and never hits a root. And therefore, the harmonic series, as you know it, diverges, right? Now, if you look at what an alternating negative does to the alternating harmonic series, here's the values now. If you start off with a negative 1, then you'll usually get a negative sum, but you can see that this definitely is not gaining or growing out of control. It is approaching a limit, somewhere in the 0.693-ish region, yeah? So the point is this, an alternating negative aids convergence a lot. Whereas the harmonic series without a negative diverges. If you throw an alternating negative in there, it does converge. And that's just one example. Some series only converge with the help of that alternating negative, like the harmonic series we just did. That only converges with that alternating negative component. When it only converges with that help of the negative, that's called conditional convergence. It converges with the condition of that alternating negative being there. Now, we'll prove conditional convergence in a later lesson. I think it's that 138. It's really easy to prove, by the way. It's great. If a series doesn't even need the help of the negative, the help, I should say of the negative, sorry, that's how I prove this, of the negative, it would converge with or without it, then the series absolutely converges. Actually, let's say it the other way. Converges absolutely. Can you give me an example of a series that converges absolutely? Okay, so I like 1 over 2 to the n. That's good, but it's about with negatives, and so that converges absolutely. If it had that, it would converge. If it didn't have that, it would still converge, all right? What about a p-series that would converge absolutely? 1 over n squared. Now again, with the negative in there, that would converge with or without the alternating negative. So you would say that series converges absolutely. Do you understand the vocabulary? All right. Let's look at what a problem or two will look like then. The definition of alternating series convergence then. If this is any series, but it's usually alternating. You don't usually talk about absolute convergence for positive term series. That's dumb and weird. So if the absolute value of the series converges, then the series converges absolutely, just like we talked about, even without the help of the alternating negative. If you have an alternating series and the absolute value diverges, then that means the alternating series doesn't converge absolutely. It doesn't mean it diverges. The series with the negative diverges. It just means it might need the help of the negative. We would need to investigate further, which we'll do later, all right? It might be converging conditionally with the negative. Let's show you what I want you to show or to do. The question is, does the series converge absolutely? Justify. The first thing you would do is say, hey, I am looking at the absolute value of the series, because that's what absolute convergence is all about. What happens when you remove the negative? Does it converge anyway? When you remove the negative, it's just 1 over n factorial. Okay? Then it becomes like a problem you've done. How would you prove the convergence of that series?
Ratio.
The ratio test. So by the ratio test, the limit as n goes to infinity of the n plus 1 to the n is the limit as n goes to infinity of 1 over n plus 1 factorial over 1 over n factorial. What does that limit pan out as? 1 over n plus 1, which is 0, which is less than 1. Now, in terms of the conclusion, we would say something like the absolute value converges, the absolute value of the series converges, so the series they ask about converges absolutely. You understand what I'm getting at? Okay. Now let's look at the next one. Again, the question is absolute convergence. So we're going to tell the person, hey, I'm looking at the absolute value of this. When you take the absolute value, the negative 1 is goners, and what's left is everything that's left. So n over n squared plus 1 is the series with the negative 1 removed. Stop me if you have a question or you disagree. Okay, how do you want to go about proving that convergence? Comparison test. Limit or direct? Limit. Limit's where it's at. So we're going to compare to whatever n or the harmonic series by the limit comparison test. N over n squared plus 1 divided by 1 over n. What is that limit going to be? You feel free to just do it mentally instead of showing all the algebra. It'll be 1. Okay? So we would conclude something like, because the limit is 1, that shows there is a correspondence between the terms, and therefore both converge or both diverge. So much writing. 1 over n diverges, so n over n squared plus 1 diverges. Now to answer the question then, I could rewrite the series, or I could just say, therefore the alternating series does or does not converge absolutely. Does not converge absolutely. You see where I'm coming from? Okay. All right. The absolute convergence is actually, I set up here, it's usually used for an alternating series. But there are times when it's not an alternating series, but absolute convergence runs correct. All right. Cosine of n over 2n is a bit of a pickle because it goes back and forth in positive to negative, but not in a positive, negative way. Cosine of n would kind of, based on the period being 2 pi, it would be positive for a little bit, then negative for a little bit, and so there might be a weird pattern to the signs. Are you with me? Okay. If you were, however, to do the absolute convergence of that, then that whole guy is taken care of. I don't have to sweat that positive negative thing going on because the absolute value would work it out. Now, this is going to go a little different. Does this converge? Before, after I took the absolute value, I said, okay, the absolute value just dumps the negative 1, and boom, I just looked at it without the absolute, right? This is going to be a little different. I'm going to keep the absolute value. And I'm going to use, what kind of test would you use? What do you think? Yeah, you think a little bit. the one test that works really well here and everything else works for you pretty bad. Direct comparison test, that's it. Who's that? Let's see, what are you going to compare? All right, now let's start with cosine. Direct comparison, let's go there. Direct comparison works really well when there's some kind of condition on one of the functions. Log is less than square root of n. Cosine is less than what? 1. Okay, so we're going to go the direct comparison test. I'll show you what we're going to compare to, but can we agree that cosine of n's absolute value is less than or equal to 1? Yeah? Okay? Excuse me. So if I divide both sides by 2 to the n, I could do that without fear of inequality changing, because obviously that's even, so we're cool. And therefore the sum of all those cosine less than the sum of all those 1 over 2 to the n's. I suppose you could have absolute value on the right and it wouldn't hurt anything. I didn't write it, but you could. And what do we know about this series? It converges, all right? So they're both positive term series that and less than converging. So by that we could say that cosine of n over 2 to the n converges because it is less than 1 over 2 to the n, which converges. Why do we say that? Why do we say that? Geometric with r of 1/2, which is less than 1. So the conclusion, don't forget the question. What's the question or the conclusion? The question is, did the series converge absolutely? So yes or no? Yes. The series cosine of n over 2 to the n converges absolutely. Now, I will say this, I used to think this goes without saying, but then I guess it, maybe not. You understand that if it converges absolutely, then it converges. Okay? It's a descriptor and it's like a subset, but converging absolutely means it converges. It has a finite sum. Okay? Yes?
How come you got rid of the e?
Oh, good question. Less than, I shouldn't have. And in fact, I should say less than or equal to. You're right, I was careless with that. Now that doesn't ruin the direct comparison test, because even less than or equal to converging is still converging, right? Thank you, I missed that. Okay. And then I'm trying to get you a little flavor for power rule here, or power series, okay? What if you have this series x to the n with x of negative 2? Does it converge absolutely or not? Well, the first thing you should do is put that in. Negative 2 to the n. Converge. Okay, now converge absolutely. Now, if I were to talk about converge absolutely, then that means that I want to look at the absolute value. And what is the absolute value of that series? 2 to the n. Yeah? The negative that would alternate is stripped away and it just becomes 2 to the n. Does that converge or not? What's the first thing you check? Divergence. So that diverges because the limit of the terms is infinity, not 0. So the series does not converge absolutely. Answer the question. Is there an x value for which it would converge? X less than 1, so negative 18. Is it negative 2 less than 1? No, not less. What? So between, let's finish that first. Between what?
Negative 1 and 1.
Yeah, between negative 1 and 1. The answer is yes. All right, now, just a second. You can actually, this is going to start to go a little off topic. X to the n actually is a function. It's a function of whatever x you put in. And every x, if I were to make a table, every x would be an infinite series. When I put in -2, I got it was infinite, so I couldn't actually graph any point at -2. The graph wouldn't exist there. But if I put in 0, for example, when you put in 0, what's the infinite series? 0, okay? I could put in a half. It would become a geometric series for which I could find the sum. And so you could actually see a function of this that's continuous, because x can be any, I know n has to be whole numbers, but x can be decimals. And so you'll see, it's not that shape, by the way, but you'll see then you could get an actual graph for that function. A function can be a series of lots of little, yes?
So if you're given the x value and there's like -2, you just do divergence theorem?
Yes. Yes, that's always the first thing you check, and that's even for non-power series cases. Try these two. Go.
We have to try it so hard.
What? Yes, sir. Uh-huh. 1 to the infinity is not an indeterminate form. Approaching 1 to the infinity is an indeterminate form. But 1 to the infinity is not an indeterminate form. So, do-do-do. Do-do-do. Joe. Joe.
Michael, realistically, it should be in his car where he's in locker, like locker and nose, Joe.
Oh, what the heck? That's not alternating at all. Come here. Oh, the question isn't absolute. Never mind. The question isn't absolute. I guess it's just, I just want to get you a power series problem here. So this is not an absolute convergence question. Oh, it does. Oh, yeah. Oh, my God. Woo. Yeah, what I'm doing. Now, actually, this is good. Pause here for a second. Now, I've been telling you, okay, do this absolute convergence stuff, right?
Yeah.
This question didn't say, does it converge absolute? It just doesn't converge. And what test are you thinking is?
Or ratio.
The ratio test. Okay, now I don't know, we haven't really used it to this point, but the ratio test has absolute value within it. And so I don't even need to start the absolute kind of thing. I can run the ratio test without even addressing that. The limit as n goes to infinity of -2 to the n plus 1 over n plus 1 factorial over -2 to the n over n factorial. I'm going to do a little cleanup on this. So wouldn't you agree that the -2 to the n plus 1 is -2 to the n times -2 to the 1?
Yeah.
Over n plus 1 times n factorial times the denominator reciprocal. What does the limit, negative be darned, what does the limit approach? 0. And so it is less than 1 and it does converge. Think about that series. This is a power series. Is there an x for which it would not converge? The question, I guess, to rephrase the question is there a base that can make the exponential more power than the factorial? There is not. The factorial wins. And therefore, this series would converge for all x's, and the graph of this would be continuous for all. And the graph would actually look like that. If we were to get into that. But we'll talk about that later. Questions on that side?
Yes.
Hey, let's go answer first, shall we? No, that's a serious word. So yeah, don't worry about it. You could have asked that. Were you worried you were going to look stupid?
Yeah, I just learned about it.
No, I just throw it around like you have. Does that bother you? Okay.
Yeah, C and D on the last page.
We throw some answers up and maybe do a few questions. We'll see. All right. So are you feeling C-A-B-E?
Yeah, I don't know that yet. C-A-B.
C-A-B-E. Cave is the
Yeah, I
first.
got that.
C-A-B-E.
And it took time.
We? Okay. For 5, here's my tangent line. Y plus 7 pi over 12 equals -7 root 3 pi minus 6 over 7 pi minus 6 root 3 over x minus 7 root 3 pi over 12. Okay? Okay.
You got that.
This, hopefully, you arrived at a formula for polar arc length of something like this.
I didn't like this.
That is okay. Those are thetas, by the way. All right. Is that all on this? Yes. Okay. This bad boy. Did you get dr dt is greater than 0 on 0 to pi over 3 and pi to 5 pi over 3? I don't hear a lot of agreement there. That's too bad. Okay. B. This is equivalent to roughly -2.221. Interpreting that, that means at theta equal 1.3, the particle is moving toward the origin. Because r prime is negative, so r is decreasing.
Are there any like units like for like 2.221
No,
axis per radius?
I have not seen one with units. No.
I
Good
tried
question.
doing units and I was like,
C, my tangent line is something like y minus 0.513 equals negative 2.877 x plus 0.2349, so it might be 235. Some of those you might be different on the third decimal place because I truncated, not rounded. Okay, how'd those go? The theta at which I had a horizontal tangent, it says it says find a theta. I saved you some time there because truthfully there are 1, 2, 3, 4 thetas. If you have any of them, I am down. You did not have to find all of them, so any of these would suffice. Okay? The theta which there's a, by the way, when you find a horizontal tangent, you want to know where the top is 0, which means dy d theta is 0, right?
Yes.
Vertical tangent would be the denominator of the slope is 0. That means dx d theta is 0. That was, again, I had 1, 2, 3, 4, 5. The first one is 0.7038, 1.836. If you found those two, then you probably are doing things correctly, or either one of those two. F was the hardest one on this sheet. The answer, I think, anyway, was 22.0884. And the gotcha to that is if you thought, well, what the heck, I thought I was good at that. It is because there is shaded area that can be double counted. If you just crank out 0 to 2 pi, you just double counted several areas. So that's enough. If you got 25.1327, you obviously have some good knowledge, but you double counted several areas. The arc length of this curve is 73.08. Do I? What? Yeah. So it's doggone hard to find this point here because it involves finding the intersection of a curve with itself. That's not easy to do. It took me quite a while. And Ian Whitney didn't even help. He just said, nope. Yeah, that's not like doing it at all. Yeah, I can show you, but we'll have to come back to that. That's hard. Okay, let's go to this guy. Oops, I didn't calculate that. Oops, I threw away my last year's key. Oops. Maybe I have these. I didn't have my calculator out. I was doing these, but I had last year's. Okay, so here we go. Did you get something like 1 minus 2 sine 2 theta over 2 root theta plus cosine 2 theta? Yeah?
I thought the 2 would cancel out.
Nope.
I thought it was 2 round the whole 1 minus 1.
Find the angle that corresponds with an x of 0.5. I got that x was roughly 0.90987.
I just didn't notice that.
C. What does that say about r? If dr dt, dr d theta rather, dr d theta is negative, implies that the curve is getting r's. So I don't know. I said it this way: r is decreasing, so the curve is getting closer to the origin. Or points are approaching the origin. You with me? All right. D. Where's my D? I have the absolute min was at 5 pi over 12. Okay, I did an extreme value theorem. I looked at endpoints and critical numbers. I had 2 critical numbers. And then the fat. This was actually the free response in 2014. Polar happened about half the time. Half the years you'll get a polar free response and half the time not. I'll show you last year's. That's a good question. I'll probably take it at some point. Maybe take the. I've already used some of these. A is 9.7079. Yay. Yay. B is -3 halves minus root 3 over 2. Yay.
I use the calculator.
No calculator. C, -2. Oh yeah, A was calculator, sorry. Did you really need a calculator for C? Come on.
No, I didn't, but
Oh, that's right. C was -2. And D was -6. I think. Okay?
Okay, I just want to turn this in like the mouse, 'cause
Did I? Yeah. Okay. Do we have time to do anything? We have 1 minute. You have any questions? C?
yeah, like,
Oh, no.
I have to go to physics for 7 hours, so I can't like
Well,
get
I'm not going to
perfection.
grade you for perfection, just that you try. Well, if you so much you do it, then you deserve to be paid. Bye. Have a great day. Bye. See you later. Take your grousing outside the room. Nobody wants to hear it.
Yeah.
Get a Kleenex on your way out.
One more day?
Nope. Grab some tears. Cry on the way out. I did learn.